In 2017, a strange object entered our solar system from interstellar space. It was the first visitor from beyond our sun ever detected, and when astronomers studied it, something did not add up. It was accelerating, not from any gravitational pull they could identify, not from outgassing like a comet, just accelerating, as if something was pushing it. Harvard astrophysicist Avi Loeb published a paper suggesting the object, named Oumuamua, could be an artificial construct, a piece of technology from another civilization. The scientific community pushed back hard. The debate has never fully closed, and that single strange object from the dark between the stars quietly forced a question that most scientists now take more seriously than at any point in human history. Are we alone? And the answer, based on what we now know, is almost certainly no. Welcome to Space Review, where we follow the science wherever it leads, even when it leads somewhere uncomfortable. If you are not subscribed yet, hit that button and the bell. We publish deep dives like this one every week, and this topic is one we are going to keep returning to as the discoveries keep coming. For most of human history, the question of alien life was considered philosophy, not science. Something for late-night conversations and science fiction writers, not serious researchers. That has changed dramatically in recent decades. Today, some of the world's most respected scientists at institutions like NASA, the SETI Institute, MIT, and Oxford are dedicating their careers to the search for life beyond Earth. Not because they have found it, but because the evidence pointing toward its possibility has become too compelling to dismiss. The shift did not come from a single discovery. It came from an accumulation of findings, each one quietly widening the boundaries of where life might exist and how common the conditions for it might be. To understand why scientists now believe alien life is not just possible, but probable, you have to understand what those findings are, what they mean, and what questions they still leave unanswered. Start with the scale of the universe, because nothing puts the question in sharper focus. The observable universe contains an estimated 2 trillion galaxies. Our own Milky Way alone contains somewhere between 100 and 400 billion stars. And thanks to missions like the Kepler Space Telescope, we now know that most of those stars have planets. The conservative estimate is that there are at least 1 trillion planets in the Milky Way alone. Across the observable universe, the number of planets likely exceeds the number of grains of sand on every beach on Earth, combined several times over. Now consider that astronomers have identified thousands of planets sitting in the habitable zones of their stars, where temperatures could allow liquid water to exist. Consider that water, carbon, nitrogen, and the other basic ingredients of life are not rare. They are among the most common elements in the universe, forged in the hearts of stars and scattered across galaxies by supernova explosions. The raw materials for life are everywhere. The conditions for life appear to exist in enormous numbers of places. The idea that out of a trillion planets, only one managed to produce life is, statistically, one of the most extraordinary claims a person could make. And extraordinary claims require extraordinary evidence. We do not have that evidence. What we have instead is the opposite. Growing evidence that life's ingredients are common, and growing evidence that life itself may be far more resilient and resourceful than we once assumed. For most of scientific history, the definition of a habitable environment was essentially a description of Earth: moderate temperatures, liquid water on the surface, a stable atmosphere, sunlight as an energy source. That definition quietly assumed life could only exist in conditions similar to our own. Then scientists started looking more carefully at the corners of our own planet, and everything changed. In the 1970s, researchers discovered communities of organisms thriving around hydrothermal vents on the deep ocean floor, in complete darkness, at crushing pressures, feeding not on sunlight, but on chemical energy from the vents themselves. These were not marginal, struggling life forms. They were entire ecosystems, abundant and complex, operating completely independently of the sun. Since then, the list of extreme environments where life has been found on Earth has grown astonishing. Microbes living inside rocks in Antarctica, where temperatures rarely rise above freezing and UV radiation is brutal. Bacteria surviving inside nuclear reactors, absorbing radiation that would kill a human in seconds. Organisms living in pools of nearly pure acid. Life found kilometers underground in total darkness, feeding on hydrogen produced by chemical reactions between water and rock. Life has been found in the upper atmosphere, in the Dead Sea, in boiling hot springs, in the driest desert on Earth. Each of these discoveries expanded the definition of where life can exist, and each one made the universe look more hospitable. Because if life can thrive in nuclear reactors and deep ocean vents and Antarctic ice here on Earth, then the range of environments on other worlds where life might gain a foothold becomes dramatically larger. The most exciting implication of all this is that we do not need to look to distant stars to find plausible homes for alien life. They may be sitting right here, in our own solar system, close enough to visit. Europa, one of Jupiter's moons, has a global ocean of liquid water beneath its icy crust. The ocean is kept warm, not by sunlight, but by tidal forces generated by Jupiter's immense gravity, the same kind of energy source that drives hydrothermal vents on Earth's ocean floor. Europa's ocean has likely existed for billions of years, is in contact with a rocky seafloor, and may contain all the chemical ingredients needed for life. The Hubble Space Telescope has detected water vapor plumes erupting from its surface, suggesting the ocean below is active and dynamic. NASA's Europa Clipper mission, launched in 2024, is currently en route to investigate. Enceladus, a moon of Saturn, is even more dramatic. The Cassini spacecraft flew directly through plumes of water vapor erupting from its south pole and detected complex organic molecules, molecular hydrogen, silica particles, and signs of hydrothermal activity on the ocean floor. Every single one of those findings is a tick on the checklist of conditions scientists associate with life. Enceladus is actively broadcasting its interior chemistry into space. We flew through it, and what we found was striking enough that astrobiologists consider it one of the most promising targets in the entire solar system. Mars sits at the other end of the timeline. It once had liquid water, a thicker atmosphere, and conditions that may have supported life billions of years ago. Whether life ever arose there, and whether anything might survive in subsurface refuges today, is one of the central questions NASA's Perseverance rover is actively investigating. The samples it is collecting from ancient lakebed sediments may contain chemical signatures of ancient life, and a future mission is planned to bring those samples back to Earth for detailed laboratory analysis. Here is a fact that rarely gets the attention it deserves. The building blocks of life are not just common on Earth. They are found throughout the universe. Amino acids, the molecular units that proteins are built from, have been detected in meteorites. The Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, only 19 of which are found in living organisms on Earth. Complex organic molecules, including sugars, alcohols, and even the components of RNA, have been found in interstellar clouds of gas and dust. In 2023, researchers detected dimethyl ether, one of the largest molecules ever found in space, in a star-forming region. The chemistry of life, it appears, begins long before planets even form. There is also a concept called panspermia, the hypothesis that life or its precursors can travel between planets and even between star systems, carried on asteroids and comets. It remains unproven, but it is taken seriously enough that researchers have tested whether microbes can survive the pressures of impact ejection, the vacuum of space, and the heat of atmospheric entry. Some can. The possibility that life, once it arises somewhere, might seed other worlds, is not science fiction. It is an active area of scientific research. The pace of discovery in this field has accelerated sharply in recent years, and 2023 and 2024 produced several findings that moved the needle significantly. The James Webb Space Telescope detected carbon dioxide, methane, and water vapor in the atmosphere of K2-18b, a planet about 120 light-years away, sitting in the habitable zone of its star. More controversially, researchers reported a tentative detection of dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms, specifically marine phytoplankton. The claim is contested and requires confirmation, but the fact that Webb can even attempt this kind of detection for a planet more than 100 light-years away is a landmark in itself. Closer to home, data from the Curiosity rover confirmed that Mars once had organic molecules preserved in its ancient rock record. These are not definitive signs of life. Organic chemistry can arise without biology, but the preservation of those molecules over billions of years is itself significant, suggesting Mars had stable environmental conditions long enough for complex chemistry to develop. The SETI Institute, using new radio telescope arrays and machine learning tools to sift through enormous volumes of data, has dramatically expanded its ability to identify anomalous signals from space. While no confirmed signal of artificial origin has been detected, the technology now being deployed is orders of magnitude more sensitive than anything available a decade ago. If a signal is out there at detectable intensities, the tools we now have give us a genuinely meaningful chance of finding it. If life is discovered beyond Earth, even a single microbial cell on Europa, or a fossilized chemical signature on Mars, it would not just be a scientific discovery, it would be a civilizational turning point. The implications ripple outward in every direction. Philosophically, it would mean that life is not a miracle unique to Earth. It is a process, something the universe does when conditions allow. And if life is common at the microbial level, the probability that intelligence has arisen elsewhere at some point in the history of the cosmos becomes difficult to argue against. Scientifically, a second independent origin of life would allow biologists to compare two entirely separate biochemistries for the first time, revealing which features of life are universal and which are specific to Earth. That would transform our understanding of biology at its most fundamental level. And practically, the question of how humanity responds to confirmed contact with an extraterrestrial intelligence, assuming it ever comes to that, is one that philosophers, governments, and scientists are already thinking about seriously. The United Nations has informal protocols. The SETI Post-Detection Hub at the University of St. Andrews was established specifically to develop coordinated international responses. These are not the preparations of people who think the question is merely theoretical. Scientists believe there could be alien life, not because of wishful thinking, not because of science fiction, and not because of unverified sightings in the night sky. They believe it because the chemistry of life is woven into the fabric of the cosmos, because life on Earth has proven itself capable of surviving conditions that would have seemed impossible a generation ago, because liquid water oceans exist beneath the ice of moons in our own solar system, because the James Webb Space Telescope is detecting organic molecules in the atmospheres of worlds 100 light-years away, because the numbers, the sheer scale of the universe, make the idea of a single inhabited planet almost harder to defend than the alternative. We have not found alien life yet. That is the honest answer. But the question has shifted from whether life could exist elsewhere to why, given everything we now know, it would not. And that shift, quiet as it may seem, is one of the most significant moments in the history of science. The universe is enormous, ancient, and filled with the ingredients of life. The search has barely begun, and somewhere out there, the answer is waiting. If this changed how you think about life in the universe, share it with someone who still thinks we are definitely alone out there. Drop a comment below, telling us where you think we are most likely to find life first. Europa? Enceladus? Mars? A distant exoplanet? We genuinely want to know. Subscribe to Space Review, because next time we are going somewhere even deeper. A question that sits right at the edge of what science can currently explain. And the answer is not what most people expect.